Okay, up next we have Consciousness in Physics with George Musser. He's the contributing editor for Scientific American and Nautilus magazines, where he focuses on the fundamental physics and space science. His most recent book is Spooky Action at a Distance, the phenomenon that reimagines space and time and what it means for black holes, the Big Bang, and the theories of everything. He's won many awards for his writing, including the American Institute of Physics Science Writing Award, and as a senior editor at Scientific American for 14 years, he's shared 2 national magazine awards. He's going to speak to us about his recent work in physics and its implications for consciousness. Please welcome George.
Thank you. Thanks, Karen, for that kind introduction, and thanks to all of you for coming out tonight. I thought I'd offer a few thoughts on physics and consciousness. So if I were doing this 30 years ago, I would actually be done with my talk now, because actually there wasn't a lot to say. The mind has always been the domain of, well, philosophy, and then in the 19th century started to be psychology, then more recently computer science, but it's never really been the domain of physics. I mean, there's physics involved in the brain. There's at neuron levels, how electrical pulses are generated by neurons, for example, or the mechanical forces in the brain, what gives it the shape it has. That's all physics or biophysics, obviously. But what does physics have to say about the hard problem of consciousness, the hard problem of subjective experience? And frankly, the answer until recently has been, or even today, would be not much. But I think, and I'm going to argue tonight, that that's been changing for a few reasons. First, there's the sheer hardness of the problem. The idea of subjective experience and the sensation we have of a world and the richness that it presents to us is difficult, or some would have argued even impossible to solve with our current scientific frameworks. So you look to the physicists as well as the philosophers to help you enlarge your scientific framework. So maybe they can help there. Second, I think probably more significantly, we're beginning to see quantitative models of consciousness of the sort that physicists just like and that they can usefully contribute to. And I'll mention a couple of those in a minute. And third, and this will be where I close tonight, I think it's a two-way street. I think the study of consciousness can actually inform some of the deepest questions we have in physics, because a lot of those questions involve or even revolve around the nature of observation. What does it mean to observe, to become conscious of something, in other words? So why do we have subjective experience? This is the Chalmers hard problem, but obviously predates him, probably goes all the way back to the Greeks or whoever first thought about this. Couldn't we get by as just philosophical zombies or automatons? Why do we need to have this subjective experience that we do? And if, as part of that, if we knew the brain in every minute detail, we could explain our behaviors and so forth, but would we understand why we feel, why does something to be us? So the first physicists really to venture into this area, Roger Penrose was an early example, suggested we might need some new ingredient in our notion of physical reality, or perhaps a more charitable way of putting it is we need some new maybe mode of explanation. It doesn't have to be beyond physical reality by any means. Penrose argued that it's some kind of non-computability going on in our consciousness. And you might connect that with non-computability. In other words, you can't run the brain on a computer. It would be his argument in other areas of physics. And I don't think you have to agree with that proposal just to admire the audacity of it. And more maybe for purposes of tonight, it's an all hands on deck kind of situation. Consciousness is such a hard problem that you really need to bring in lots of specialties and disciplines to really make headway on it. And I think that was Penrose's great contribution. But ultimately, I think the main contribution the physicists are making today has to do with some of these models I mentioned briefly earlier. And those models argue that consciousness is related somehow to information, that there is an informational component, because what does consciousness seem within our skulls? It presents the information of the world to us, it kind of fuses it together and creates a unity of experience that we can then process and base our actions on. And you've seen information come up in a lot of theories of consciousness. Chalmers talked about it in the mid-90s, but probably most famously today, Giulio Tononi's integrated information theory idea, which has been around for maybe about a decade. There's more recent theories, such as Michael Graziano's attention schema theory, and I'm not going to go into the details of that for lack of time, but let me note, first of all, that Chalmers is a philosopher of mind. Tononi and Graziano are neuroscientists. They're people work in a lab or in the clinic. And yet their theories are very physics-y theories. They attempt to explain consciousness in a physicist kind of way, namely from first principles. What are the basic axioms, as it were, that go into consciousness, and then you can explain the rest out of, as opposed to kind of going the other direction, kind of a top-down approach where you look at the different faculties involved in consciousness and try to kind of pull out an explanation from that. So it's actually quite complementary to the work that Heather will describe when she comes up here on the stage. Now, that word information, I think, is crucial here. It connotes that we should be focusing on the organizing principles of the brain, and somehow the mind will be situated in that. Now, for a physicist, that's kind of music to our ears, because we think about emergent properties and collector properties of all sorts of systems, and the paradigmatic case is states of matter, phase transitions, so boiling, freezing, so-called critical points that are less familiar, where different types of like liquid and gas, for instance, blend into one another. And one of the properties of those phase transitions is long-range correlations that, for instance, when, to take a simple but not quite accurate example, but when you boil something, you start with little bubbles and get bigger patches, and soon the whole kettle of water is boiling, and the kind of order is growing from a small scale to a large scale. And you see that actually in all sorts of different phase transitions, and also perhaps in the brain. The brain it's acting as a cohesive whole to produce the unity of conscious experience that we have. Also in physics, we have a principle of universality, that it kind of doesn't matter what a system is made out of, it exhibits the same behavior. And perhaps the same is true, as John mentioned, of consciousness. It could be made of neurons, as we are, but maybe of logic gates, silicon logic gates, or what have you, or some entirely new type of component ultimately. So Tononi's theory, the integrated information theory, really runs with that idea and constructs or analyzes abstract computational networks and see how the information flows around them or is integrated. And it's not a complete theory. In fact, theory is demonstrably wrong in some ways, but physicists aren't put off by things that are wrong. They like to develop that, and maybe there's a germ of truth in them, even if the theory overall is incorrect. Now, what's interesting, and this is actually where it connects with the topic of my last book, the role or the models of consciousness that we develop can kind of work the other way. It's a two-way street. They can help us understand these big problems that we face in physics. And one question that Tononi has had to confront in the development of his theory is to explain why some systems or even some levels of a system are conscious and others are not. So why is the cerebrum or the cerebral cortex conscious, and why not the individual neurons or the individual brain regions or the individual enzymes within the neurons? Why is consciousness at the level that it is? So they've actually been developing a whole theory of basically causation and how causation works in an integrated and hierarchical system such as the brain. And that theory of causation, I think, is very interesting from a physics point of view, because we face the similar situations in physics. Where do we ascribe causation in the world? I mean, conventionally, in a reductionist paradigm, we put it at the lowest level. We say the real world is actually happening at the particle or even deeper level. And the rest of us are just kind of sitting on top of it, going along for the ride epiphenomenally. But I think we can have a more nuanced view of causation, and Tononi's theory helps us with that, that you can actually, what we do may influence what the particles do. You can have causation in a more nuanced and bidirectional way, perhaps. And what's, again, fun for a physics, some of the physics point of view, is they develop a mathematical theory to partition causation among these different levels of the hierarchy, which is kind of cool. If you can put a number to it, then maybe there's something to it. So another way that consciousness and the questions it raises within neuroscience can help us in physics are, again, some of those fundamental questions in physics. And frankly, physicists, we were pretty slapdash about what it means to observe something, what it means for an idea to swim into our experience. Because our conscious experience is what we have to work with. We sometimes forget that it's actually not the mystery. The world, the objective world, is the mystery, and we have to process it through our subjective experiences, as Descartes pointed out. And often we, in our theories, I create an idealized observer that doesn't correspond to anything in the real world. This idealized observer, for instance, stands outside the system that we study. So when you do an experiment, you're here and the experiment's there, and you're not part of the experiment. It's over there, and you can analyze it in a controlled way. But of course, it's never that way. You influence it, if only by your gravitational field. You're influencing the experiment, but probably in a more profound way. We're part of the system that we're studying. And this comes up especially in quantum mechanics, so that's near and dear to my own heart, and things that I've worked on. So Schrodinger's cat, the cat that's alive and dead at the same time. We don't see that in the real world, but the theory says cats can be alive and dead at the same time. We see them alive or dead. So particles, they can be here and there at the same time, but we see them only here or there. So there's a kind of a grammatical transformation occurring where the ands are all searched and replaced by ors in physics. And how does that happen? And a century after this question was first formulated by Einstein and Bohr and the others, there's no answer to it. There's an aspect of that question called the preferred basis problem. It doesn't give as much attention, but perhaps should. And that's that even the categories, alive, dead, here, there, don't exist in our fundamental theories. They don't come out of any kind of deeper understanding of the world. So where do we even draw these lines that then we say the particle's here or there, the cat is alive or dead? We have to construct the categories that allow us to create those kinds of distinctions, and our theory doesn't help. So we're hoping the neuroscientists can help us, the physicists, with this kind of question. Maybe these categories are determined by the structure of thought, almost like in a Kantian type of philosophy. Anyway, I'll just close with that idea. And the bottom line is that observation is a conscious act. Just by definition, everything in the world is filtered through our subjective minds. And we need in physics a notion of that to make sense of objective reality. We need to know subjective reality to understand objective reality. And hopefully, in the course of developing such an understanding, we can help the neuroscientists with their problems as well. Thanks.